Hi everyone, happy Halloween. Thanks for coming. I'm very happy to introduce Karen Yeats, who is a professor in our department and Canada Research Chair in Combinatorics in Quantum Field Theory. Their research covers, I think, lots of different combinatorial problems that pop up in physics and quantum physics in particular. I'm sort of hoping their talk is not going to be as scary as I advertised in the seminar email. Please.
All right, thank you very much. So the people who are at FIPSAC have already seen this talk. Up here at the top, quantum field theory has come up, and I've given talks before here in Tutte and other times on various parts of that, and these are all represented by some pictures here. I've given talks on that and on that. Anyway, but that's not what we're going to talk about today. Today, we're going to talk about causal set theory. And this is sort of slightly weird because some time ago, Jane talked about causal set theory and actually talked about a particular research result, but I'm actually going to give an overview talk about why causal set theory is something that I, a few years ago, recently got really excited about, and why I think maybe you might be really excited about it too if you knew a little bit more about it. So this is very much an overview talk, and it will, other than mentioning, well, it won't talk a lot about things I have personally done so much, a little bit. Okay, so it's just that little story, not those other stories. I also apologize for not using the boards. I love the boards in here, but I already had these slides, and I didn't have so much time to boardify it. Okay, so what are we going to talk about? So one day, this is quite a while ago now, well, a few years ago now. It must have been before COVID, actually, but that's only because COVID is like a complete blank in my memory, and I don't know what happened then. So it feels like recently, because there was like a discontinuity. Anyway, I was sitting in a quantum gravity talk, but it actually ended up being a POSET talk, which I was not expecting when I went to this talk. And here's the story for how that happened. So you might have seen a space-time diagram sometime in your life. So you got to imagine, I'm going to draw my pictures in 2 dimensions of space-time. So there's 1 dimension of time that's going up this way, and there's 1 dimension of space. It's the other way. And this is me, and I'm sitting here, all right? And I don't know what sort of things you know about space-time, but one thing you might know is that if I send off some light, it goes off at the speed of light. So here I've got some light. This is the light cone. So there was some light coming in from the past to me and some light going out in the future. And I'm going to always draw my light at a 45-degree angle because I'm going to use units where 1 unit of space and 1 unit of time kind of line up. So those are good physics units. Okay, and now what's interesting about these space-time diagrams, you have to imagine, and this is where you're in some sort of class about relativity, and you've got friends, and they're on spaceships, and they're all like going by each other. So you have a friend, this is your friend, on this spaceship, and so here's the spaceship, and your friend on the spaceship passes you at some point, and now here we're somewhere over here, and the person on the spaceship is going slower than the speed of light, so that's good, right? Okay. And you see this person on the spaceship, and from your point of view, this person on the spaceship is over here at this x-coordinate, right? Okay. And over here at this time coordinate, right? Okay. That makes sense? Okay, but what about the person on the spaceship, right? This is where you got this science fiction story, and the person goes on the spaceship at close to the speed of light, and they go all the way over here, and then they come around, and they come back, and they're still going close to the speed of light, and now everybody is dead, right? That's not so good. And why does that happen? That happens because this person on the spaceship is accelerating at a constant velocity, so this is really acting like they're not the point I should have. That's not the point I should have put for my point here. Whatever. We'll get back to that. We'll get back to the point and its coordinates in a moment. So there's my friend on the spaceship, but they're going at a constant velocity, and so they see their time coordinate looking like this. So here's their x coordinate, and here's their time coordinate. Okay, and so now. That's kind of weird. And so now let's put another point in here. I didn't do a super good job of this, I'm afraid. So here, now from my perspective, this is at this point in x and this point in time. But now from this perspective, I have to make them parallel to these different things. So this is over here. I've got to make my things parallel here. So I get something like this point in x and this point here in time. And so you see the time dilation happening, right? I've not gone nearly so far on that time axis as the other time axis. And so you know what? I have this problem. Okay, but we're not actually worried about our friends that go away on spaceships forever and then we die. What we want to notice here is that the thing that stays the same is the light cone, right? So the speed of light, that's the same for everyone, for any observer, whether I'm on the spaceship going at a constant velocity or whether I'm sitting here and going at a different constant velocity. And if you're wondering why it's called a light cone, it's because if I had 3 dimensions of space-time or more, then it really is like a cone, right? You got to imagine it's coming out here like a cone, all right? It's a light cone. And now, the other thing that you know from your science fiction books from being a kid is that nothing can go faster than the speed of light. Not even information can go faster than the speed of light, right? That's the way it works. And so anything that I'm going to have a causal effect on, anything that I could change in some way, well, if I'm here in the middle, something I'm going to actually affect, it can't be over here because the information can't get there that fast, right? That's too close to me. Sorry, too close in time, too far away in space. I cannot get there. There's no causal connection. And everything that's in those kind of places is called space-like. Because, you know, some possible friend on a spaceship, that would be just literally on the space axis from me to that point, right? Okay, and then there's other points that are in here. And those are the points that I could potentially have some causal influence on, right? Because they're in my future. Okay, they're not literally in my future. I have to move a little bit in space. But again, you know, it's within the light cone, could do that. So these are time-like. These ones are also time-like. They're in my past. So this is the past, my past. This is my future. And the stuff that's on the light cone is light-like. Okay, so that's nice. And the point is, the stuff that's in the light cone, in my light cone, is something I could have in the future a causal effect on, or could have had a causal effect on me. And so where does the poset come from? The poset says, okay, what are we going to remember from this picture? Because I don't care about the spaceships, and I don't care about everybody dying, and all that sort of stuff. But what I am going to care about is I'm going to keep the light cone. So here's my light cone. And I'm going to keep the points. And 2 points are going to be causally related if the one is in the light cone of the other one. And so here's some points. Here's another point down here. And then maybe up here, like I could say, okay, well, this guy's got a light cone too. There's the forward light cone of that point. And so then I put another point in here, and that one's causally related to that guy. And so you see what you have is a poset, right? Here's a poset. That's connected to that. I could have some other guy out here. Maybe that's in the past of that guy, something like this, you know. And I got some sort of poset. Okay? Poset. So that's interesting. You thought you were at a physics talk, but you're actually at a poset talk. Well, you didn't think you were at a physics talk, but I did. Okay. I kind of expect everyone here knows what a poset is, but just in case, I'm going to use a less than or equal to for my poset relation. An interval in a poset is that guy there. You're interested in all the points that are between the two extremes of your interval. And intervals are important for me because we're going to say a poset is locally finite if all its intervals are finite. But in this other community, there's another way to say that. You just say it's a causal set. And that means it's a locally finite poset. So the idea is, what are you remembering from space-time? You're remembering the causal relation. Well, here we're in a, apparently anyway, continuous space-time, and there's still a causal relation, right? I'm right here right now, but now I've talked for a moment, so we're actually somewhat slightly later, and the point I'm still at is causally related to the one before. But we're also interested in discretizing this story. And the way we're going to discretize it is we're going to say it's a locally finite poset. And so that's a causal set. I'm going to use the downset upset language. So the downset generated by an element is all the stuff that comes below it in the poset, and that's its past. The upset generated by the element is all the stuff that comes later than it in the poset, and that's its future. All right, and if you prefer to say order ideal and order filter, that's totally fine. But if you're like me, you forget which one is which. So I like the upset downset language better. All right. Now, the other thing that's really important is when we move from a continuous spacetime to a discrete spacetime, well, we somehow need something. We need some very small piece of information from our continuous spacetime, because just the poset's not quite, you know, there's something else we need. And what we need is we need some notion of volume. So if we were in a continuous spacetime, we could have some spacetime interval, so all the stuff that's in the future of this point and in the past of this other point, and that's some, you know, submanifold. It's got a volume. So great, but what is that going to turn into this discrete context? It's going to turn into the number of points in that interval. So that's another good reason why we want a locally finite poset, because I don't know about you, but I don't really want to be counting things if there's not finitely many. And so the basic idea of causal set theory, well, I phrased it as a question: can this be enough? And I think there are two reasonable answers to this. We're very briefly putting on our physics hats. I'm going to give two reasonable physics answers for why you might think this is a good idea. The one is that in the continuous case it is. So for suitably nice continuous spacetimes, knowing the causal order and the volume of intervals is enough to recover the manifold. Now this is one of these things that if you actually try to pin down exactly what the theorem is, it's a little bit tough, as does sometimes happen in the physics literature. But that's why suitably nice is a little bit vague. And you can look it up. There are theorems, there are concrete theorems in this direction. So it is enough in the continuous case. And so you can reasonably ask if it's enough in the discrete case. There's another side to it, which is that even if it's not enough, it should be there. It should at least be there, even if you also need more information. And that's sort of the argument over here. So there's a paper of Raphael Sorkin from 1991 that's about forks in the road. And the basic argument there is, if you want to take seriously the idea that space-time really is Lorentzian, you want to take seriously the idea of the path integral, and you want it to be discrete, then you get causal set theory. And these are very reasonable physical axioms. A lot of approaches to quantum gravity actually work in the Euclideans. They're not Lorentzian, but like, I would really like the Lorentzian. That's what makes time special. If you're not in a Lorentzian, if you're in a Euclidean manifold, there's not really a distinguished time, right? Like, we just sort of arbitrarily choose one of them to be time. And that's not the way the real world feels, right? Like, time is really different from space. Okay. So, but I would take the argument here that, look, at least you need these. If you're going to be Lorentzian discrete and the path integral, you have a causal set. Maybe you need more to get everything you want, but at least you have a causal set. Okay, so another way to say the basic question then of causal set theory, this is their Hauptvermutung, is that if a causal set is suitably manifold-like, then up to some discreteness scale, does it determine the manifold? All right, and I again phrase this as a question. Okay. But that's all like vague blah blah stuff, right? In like the bad physics way, right? There's a lot of wonderful insights in mathematical physics, but also there's a certain amount of like just vague hand wavy stuff. And that previous slide kind of was. So let's do something concrete. Let's actually, do something. And there's a number of things you can do. And I'm basically going to spend the rest of the time telling you about some of them, a few of which I have done a few things on. So one thing you could say is, okay, maybe the causal set is not enough, but it's something, it should be there. And so if you can't recover everything you wanted to know about space-time, like, let's at least see what we can recover. We can recover surely some things that we wanted to know about space-time. So for instance, you might want to know about geodesic distance. That's the kind of thing you might want to know. And that, in some interval, then that becomes the height, a length of the longest chain. Okay. Another thing you might want to do, so let's say, again, we're in an interval or otherwise in a finite causal set rather than just a locally finite one, then I could enumerate pairs by the size of their past and the size of their future. And you could ask, is this enough to, in some sense, see something about the manifoldness? Okay, and this is an idea of Raphael Sorkin's. He was at Premier Institute, he's retired now, but he's still around and in town. And Ian, one of my students, and I, well, and especially Ian, has been thinking about some of this, about, well, what can you learn about the manifold from these two things? Another thing you might want to think about is a generating series of the interval sizes, right? So, right, like how many intervals are there of size 2? How many intervals are there of size 3? And so on. And you can turn that into a generating series and you can ask what you can tell from that. And that one's particularly interesting because if the causal set did come from a flat Minkowski space in a sense which will become clear in the next slide, then actually you can compute what the expected numbers are and, you know, in some limit, which, well, there's issues of which order you're taking some limits, but it looks like it should be some nice series that you can read off, for instance, the Minkowski dimension and other properties you might want to read off from the causal set. And so there's some work of Samati Surya in that direction, and Ian and I are also thinking a bunch about that. And well, concretely, you should ask Ian about that in 3 more weeks. There's other dimension estimators, so this question of like, let's at least recover the dimension of the underlying space, like that would be good, right? And one of the oldest ones is this one here, where you take the number of relations and normalize it in a suitable way. And with some caveats, that does recover the Minkowski dimension. There's a whole story here because there's an interplay between these different notions of dimension. Because when I stand up here and I say poset, the notion of dimension you're probably thinking about is order dimension, where you say, well, how many total orders do I have to intersect to get the poset that I'm interested in? And that's the natural notion of dimension in if I'm just abstractly thinking about posets. But the one we want here is different because we want this Minkowski dimension, and it corresponds to what the poset's dimension is as a sphere order. So if you think about instantiating it as a collection of spheres in some dimension now of Euclidean space, where the order relation is the containment relation of the spheres, you would say, how big a dimension of space do you need, or can you do that at all? And that's your Minkowski dimension. Another way of seeing your Minkowski dimension. The connection between those, of course, is just a slice across the light cone. Okay. But I keep saying this, well, what if it comes from a Minkowski space? But you don't know what that means. So what does that mean? And so this is another thing that physicists in causal set theory have been thinking about. And they call it sprinklings. So you take some Lorentzian manifold, not necessarily a flat Minkowski space, but any Lorentzian manifold, and you want to choose points on it in some way, some random way. And the correct random way to do it is to use a Poisson distribution. And the reason you want to do it that way is because you want to get this volume to number relationship to work out correctly. And a Poisson distribution does that just very nicely. And then once you've picked the points on the manifold, then you just use the induced causal order. That's what you get. There's some density parameter rho here that's determining how densely you're sprinkling. And this is something that both mathematicians and physicists have thought about. So there's a few of the mathematician names that are associated with it. And there's lots of connections to things that people, like some of you and like them, who study random discrete objects might like to think about or know about. So for instance, this is actually not a hard one to see, but just as a concrete example, if you're in a 2-dimensional causal set, so 1 dimension of space, 1 dimension of time, like I was drawing at the beginning, then the height is the longest increasing subsequence in a random permutation. And that's not actually hard to see. That's an easy result, so you can think about that if you haven't seen it before. It's just coming from the fact that in 2 dimensions, order dimension and Minkowski dimension actually do agree. It's one of the reasons 2D is so nice. And so now you're really thinking of just 2 total orders and you're taking their intersection. Well, one of them might as well be the identity. So we're just talking about now a random permutation. And if you think about it, this is the connection. Okay? Well, I said that one of the goals here was to recreate things that we would have wanted in our continuum space-time and try to build them in this causal set context. All right? Well, one of the things I might want is the D'Alembert. And you might say, I don't want the D'Alembert because I'm not actually a physicist. I don't even know what the D'Alembert is. So now I'm going to tell you what the D'Alembert is. It's sometimes called the box operator. So we'll say box. And what is it? Well, basically you want to take the square, like d by d whatever squared, for the 4 different, let's say we're in 3 plus 1 dimensional. So we got time, and we got 3 space dimensions, and we want to take all these double derivatives, but we want to do it in the Minkowski context, so the sign is going to vary between them. So it'd be like this. Okay? So now maybe you don't care about that because you don't really care about differential geometry or whatever. Fine. But physicists care about that. And so maybe you would like an analog of it on a causal set. But now you run into a problem. Because, okay, this is made out of differential operators, and I think none of us are surprised then that if I want to take a discrete analog of a differential operator, I probably want some kind of difference operator. But now I have a problem. Because remember, it's only a locally finite poset. And in fact, I'm typically going to expect infinite numbers of covers. And here's why. So suppose I'm sitting here, and here's my light cone. So somewhere up here is some element that covers me. Okay, let's make the light cone of this guy. Well, notice here that in this, this little section here, well, if you keep going, that has infinite volume, right? Like, so somewhere in there, I'm going to find a point. I certainly expect to find a point in there somewhere, right? So somewhere in here's a point. Okay. Now that's not in the forward light cone of that other point, but it's definitely in the forward light cone of me, so that covers me as well. Okay. Well, now let's do that again, right? There's still a non-zero volume in there. Okay, I didn't draw my lines very parallel, so I'm probably not that right now. But if the lines are parallel, there would definitely still be infinite volume in there. So there's another point in there. Okay, but as long as you're not actually on the light cone, no matter how narrow this strip is, eventually, if you go out here, you should expect to find a point. And so it's not just that it's allowed by the axioms, but it's actually the expected situation that you have infinitely many covers. And so any sort of difference operator that's using covers as nearest neighbors is probably going to run into a problem, right? You don't expect it, well, to be well-defined if you're thinking in this case, or if you're working with finite cases and hoping to take a limit, you're not expecting it to converge. That's going to just be bad. And so what's the answer? Well, the answer is you can use an alternating sum, and if you do it right, things will cancel, and you'll get something nice and finite. Isn't it nice when that happens? And so again, this is in 2 dimensions, so 1 plus 1 dimensions. This is due to Raphael Sorkin from 2009. Faye Dowker and, shoot, I don't remember the first name for, anyway, and Benincasa in 2010 worked this out for 4 dimensions, but it actually works in general, and that's a result due to Dowker and Lille-Glaser. But these are the coefficients. So I said you have to take alternating sums. Alternating sums of what? So you've got the covers, so that's height, size 2 intervals. And then you're going to subtract off something about size 3 intervals. And then you're going to, add on something about size 4 intervals and so on. And the coefficients you need to do that are going to vary depending on the dimension. So I've only written up to dimension 4, and the C's are just the coefficients. But okay, this is another one of these cases where you're me or someone like me, and you're sitting here, and it's a physics talk, and you're kind of like this in the physics talk, and then there's a table of integers. Well, okay, that's not quite integers, but like I can fix that, right? It's easy to make those into integers. I mean, what's this calling out for? It's like calling out for a combinatorial interpretation, right? Like I got numbers. They're not positive, but the signs are clearly under good control. They're not actually integers, but the denominators are clearly under good control. Like this should count something, right? And in fact, you don't even have to just intuit it off the table of numbers because Lou Glaser gave a formula, now an alternating formula. So to compute each one of these individual coefficients, they gave an alternating formula. And the alternating formula is already built out of the right kind of pieces to make it easy to do a combinatorial interpretation. Because there's some binomial coefficients and there's some ratios of gamma functions that if the right things are even, also is a binomial coefficient. And if the things are not even, well, you know, you got some odd factorials in there. But like, that's pretty nice. And yeah, that's pretty nice. So you can do it. Do you want to know the answer? I can show you something that counts. I mean, you could probably pick whatever your favorite thing is that's counted by binomial stuff. Or in fact, after you work through it a little bit, you can pick your favorite Catalan thing probably and put your favorite Catalan thing together in the right way. And you can get something that'll work. This is the first one I found that'll work. It's a little bit tricky because it is alternating, and so you have to find some explicit way to embed the ones in the others so that it all cancels out and blah, it all works. But you can do it. I kind of want to put it on the board instead of in that little space. I'm going to put an example on the board. Because what you end up doing, my favorite Catalan object is non-crossing chord diagrams, because I really like non-crossing chord diagrams. Now, what you end up needing here is not just your favorite Catalan object, but you end up needing some suitable sequence of your favorite your favorite Catalan object. So I'm going to start with a rooted partial chord diagram. And what am I going to do with my rooted partial chord diagram? So there's going to be some Catalan pieces, essentially. So, okay, now I have to make sure I get even numbers of things inside. So we're going to do something like this. So we're going to have 3 kinds of chords, the just plain ones, which are white because I'm writing on a blackboard, and the colored ones. And they're going to have the property that, so the white ones are always inside the colored ones. We can make a well-defined notion of inside. And everything outside of the colored ones is just a dot, and there are no just dots inside. So it's really just a sequence of my Catalan bits and my dots. Okay, so that's enough blabbing. I just have to actually make an even number, because otherwise it won't. Otherwise I will clearly have a problem, right? You know, something like this. Something like this. I could do another one. No, like that. Doesn't really matter. Stuff like this. Okay, are you sick of it yet? Okay, and then I need one additional piece of this story because to make the explicit cancellation between these things work out, the key thing you're going to need to do is we're going to need to think about the sizes of each of these. So this one sort of has size 3, right? There's 3 chords involved in this. So I sort of imagine there's 3 insertion places here. This one has size 1, so there's like 1 place I could put things before it. This one has size 1, 2, 3, 4. This is going to be 4 insertion places. Anyway, so you play a game like this. You can use these insertion places to do some explicit cancellation, and you get basically a class of these guys with some conditions on where there are runs of large numbers of dots coming before the Catalan blocks. And those give you those coefficients. And then you're done. So that's kind of fun. Okay. Now I want you to put your physics hat back on for a moment. Because, okay, we were having fun, right? What were we doing? We were playing with posets. We said, yeah, we like locally finite posets. And then we said, okay, let's try to read properties off the locally finite posets. And then one of the ways we thought about trying to do that is we said, well, if it had come from a Minkowski space. Oh, I should say, those things that cancel, they really do agree with the D'Alembert if your poset had come from sprinkling on one of these flat Minkowski spaces. That's the sense in which it's the right answer. Okay, but there's a problem here. Because look, if I'm trying to use this as a model of space-time or something I want to do quantum gravity with, I don't want to start with my Minkowski space and then do something, right? The whole point is like, this is supposed to just be the macroscopic, stupid garbage stuff that isn't really there, right? Like I should start with the poset, right? That's how it should work. So it's kind of unsatisfying to sprinkle. You can do some really cool mathematics, and people have, and people will continue to, including Jane. But, well, maybe, actually, you're about to come out. You're on the bottom of this slide. But it's not really fully satisfying. So you might ask, maybe I can get what I want just by somehow picking a random manifold, by picking a random poset in some suitable way. All right? And now the first way you might think is, well, how about of all the posets of size n, let's just pick one uniformly at random. Like that's a good way to pick a random object, right? A random discrete object. In this case, that doesn't work. And the reason is actually very classic due to Kleitman and Rothschild in 1975. It's that the ones that dominate in that case, okay, I don't know why I've still got light blue on, let's use a better color. They actually look like this, that a half of the elements are here in the middle, a quarter of the elements are up here at the top, another quarter of the elements are down here, and there's a 1/2 probability of each of these possible relations going in here. So those guys dominate if you're just taking uniformly at random of posets of size n. And that's not a very good model of space-time, right? There are exactly 3 times. There's now, there's then, and there's the future. And that's it. And like, that's not like this. And in fact, this almost killed causal set theory. Right? People noticed this, and then a lot of physicists were like, well, that's a stupid model of space-time. Let's go home. But that's not fair either, because this is not the only way to choose a poset at random, right? And so one of my messages to you is if you have a model of random posets that came up in some totally different context, how about a question you can ask yourself, is that a good model of space-time? And I think that's a really interesting question, because I don't think we've found the correct way of generating them nicely. But one of the things people do, physicists have been doing, is using growth models, where you generate your space-time one element at a time. And so the most obvious thing to do is this one, where you just start, okay, good, I got a vertex. Okay, what can I do? Well, I could put another guy that's in its future, or another guy that's not in its future. Those are kind of the 2 things I could do, right? And then after that, what can I do? Well, I'm actually going to make these labeled for the moment just so that you can see which one is the new one most easily. Because now, what else could I do? Well, I could add another guy here. Or I could add another guy on top of either one of those. Or I could add another guy on top of both of them. Or I could come over here and I could add one that's incomparable to both of them. Or I could add another guy that's on top of both of them. Or, wait, what am I missing? Oh, I know what I could do. I knew there was one more and I was not seeing it for the moment. I could do this guy. Okay? Those are the possibilities. And, you know, keep going. Okay? And you can do this a nice way. You can say, okay, well, I'm going to say it's probably probability p to go this way, and then like q, which equals 1 minus p to go that way. And then something interesting happens when you try to go up to this one, because the right way to set this up, there's 2 ways you could get there. Because what you actually want to do is you want to take a subset of the elements that are already there and put your new element on top with probability p to the size of that subset. There's 2 ways to get this one. Because I could have taken just 2 as the subset, and I have to take the transitive closure, so then I get that guy. Or I could have taken 1 and 2. So if I think about what probability should sit on this line, there's two things. So you could be comparable to one of them and you could be, wait, what am I trying to say? You could be comparable to one of them, or you could be comparable to both of them, but then you have to take the transitive closure. So that's this guy, which is just P. I think I did that right. Okay. So in this community, this process is normally known as transitive percolation. But those of you who do random graphs will have recognized that it's also what's known as a random graph order, where you just take the usual Eder-Schwendian random graph, but you order the vertices, and now you think of it as a directed graph going from small to large, and then you take the transitive closure, because that's what I just said you should do, right? So this is something that exists. And look, lots of names. I wrote down some names of like really famous people who study that sort of stuff because they've studied that, because it's just a random graph order. And if you were here, was it last year, Jane, that you talked in Tutte about? Yeah. So last year, if you were here, Jane actually talked about a result instead of me who's just blabbing on. But it was from this context that we'd been learning some stuff about causal set theory because I was excited about causal set theory. And there are some very natural questions that fit in with her expertise. And she told you about them last year. All right? So that's cool. Now, what else can you do? So if you allow yourself to weight differently, because I said I was just going to take P to the size of however many elements were in the element that I put my new guy on top of. But I don't know, if you're putting on your enumerative hat for a moment, I'm sorry, you have to have a lot of hats in my talks. But it is Halloween, so it's a good day for hats. If you put on your enumeration hat instead, you might say, why don't I just have a different variable for every possible size of that guy? And you can do that. And you can make that work, and you get a similar family. And in the causal set community, they're known as classical sequential growth due to Rideout and Sorkin. And these end up being a nice set of models because they're the most general models that's, you can set up some axioms rather than just saying, well, do it this way and see what happens. And the axioms correspond to something that's called general covariance, something that's an analog of Bell causality. So I guess an analog of covariance, an analog of Bell causality. So again, if you're a quantum person, those are like things. And the gregariousness is just a non-triviality. Basically, you want to have a non-zero probability that you add something that's incomparable to everything that already existed. And that one's not a big deal. If you don't have that one, then you just get some extra trivial stuff. And you know what? I didn't mention anything I did, but I did do something slightly in this direction. Am I reading the clock correctly? OK. Because something I did ages ago, like something I've done that's other part of my story is these combinatorial Hopf algebras and Hopf algebras of rooted trees. But you could also actually do a Hopf algebra story on posets. And this kind of fits into that context in a kind of cool way, but I'm not going to talk about that. I'm going to talk about something else, which is I want to look in more detail at covariance. Because I didn't tell you what that was, other than to say that covariance is a word that if you were a physicsy person, you would know. OK. But in this context, covariance basically means unlabeled. And here's how you want to think about this. We're here in the world. And this point does not have a different label than this point. And the world is not different if I switch them, right? Like, the world's not labeled. We're working in an unlabeled world. Now, OK, I just said it had covariance, but it has this general covariance, which is a sort of like it's all label independent in the end. Like, it has labels, but like if you take a infinite path through that tree or whatever, you don't, like, it's all the same. So it has a kind of covariance. And that ends up meaning that the analog of the observables are covariant. So that's good. That's like a minimum. We would definitely want that. But really, it would be nice to have covariance throughout. It would be nice to be working with unlabeled posets from the start. OK. So now you say, OK, come on. You're making this way more complicated than it needs to be. Because I know how to do this. Like, this would already be easier if it was unlabeled. Because look, this one is the same as this one, and that's the same as that one, right? Like, come on. Just put them together, right? You can do that, for sure. What do you get? You get a poset of posets ordered by downset relation, right? Like, that's nice, poset of posets. But if I'm trying to do this kind of random generation game, I don't like that quite so much because it's not a tree anymore. It is really nice to have a tree when you're trying to do one of these growth processes. And so if you want covariance throughout, you could do that. But if you want to keep treeness as well, then you end up with something that's known as covtree. Okay, and I will tell you a little bit about covtree. So I'm still going to start with that guy. Actually, I'm going to start with the picture from the other page, and then we're going to fix it. That's what we're going to do. So what was really the problem? The problem here is that we had 3 copies. Right? We have this copy, and this copy, and this copy. And we don't want those 3 different copies. And the reason why those guys came up twice is because in the set of downsets of this, these guys, that has that as a downset, and this one has that as a downset, and this one has that as a downset. Okay, those are true facts. Why do I care? I care because what I'm going to do now is I'm going to upgrade this to not be about individual elements, but to be about sets of the elements. So I'm going to clean this up a little bit, and then I'm going to write some things on the board. So this little guy, it's not got a 1 anymore. It's just going to sit by itself in a set. Perfectly good. Now over here, let's take, like this one was okay. And this one was okay, because it didn't have more than one thing. The only thing that it has as a downset of size 2 is this guy. So these ones, they're still kind of okay. Oh. They were okay until the eraser decided to not work. There we go. Now they're okay again. Right? So that guy can live by itself in a set, and this guy can live by itself in a set, and they can live on top of this guy, which is living in a set, and this guy's still living on top of that guy. So that part's good. I'm happy with that part. I'm also happy with these other 2 guys on this extreme. They're fine. They are not bothering me. And they both live on top of this guy. And none of those things bother me. I'm just going to take off their labels. So this guy's living by itself in a set. This guy's living by itself in a set. This guy's living by itself in a set. These are both on top of that, and that's on top of that. Now these guys, okay, well they're all the same now. So let's just draw it once. All this garbage. Get rid of the garbage. So there's this guy, just 1 copy. Now what does it lie on top of? What I'm going to put inside is the downsets of size 1 less that that guy has. And this guy has 2 downsets of size 1 less. This one and this one. That was the central problem. And so now what naturally has happened is the nodes of my tree are no longer just single posets. They're now sets of posets of the same size. And I can have some up here on the other layers too, right? I can have something like this. Like I could put these 2 together in a set. That's also okay. And it's still the case that the only downset of size 1 less is that guy. I could also, for instance, put 2 things in here. I could put something like this. That's a set of posets of that size, and it has those guys as downsets, and so on. So I'm not going to draw the whole thing because it gets huge. Okay. Make sense? So here's what we're going to draw on the board again. Because here's a question you could ask. Because what's going on, we have something like this. So these are unlabeled posets of the same size. So we'll just call that size n. Oops, this is n, size n. And I'm going to say this is a node of covtree. If there exists some poset Q such that this set, which I didn't give a name, so I'll just write it again, is the set of unlabeled downsets of size n of Q. Now that doesn't always happen. You can have sets P1 through Pk that can never appear as a Q. So like not this guy. If I put this guy here and that guy, if you're very bored, you can think about why there is no Q that could have exactly these 2 as the set of unlabeled downsets. And so now this is now a purely combinatorial definition. There's no physics in here. And so you could ask questions that you might care about from a physics point of view. Like, it would be nice to have a good way to see, to recognize the elements of curvature. It would be nice to understand them better in all sorts of ways. And so I said I wasn't going to say much about things that I've done, but one of the things I've done with some of my students, plus a colleague in the UK, is, well, think about things like, okay, suppose there is such a Q. Can I give a bound on the size of Q in terms of n and k? And it's not what you might first think, but it's also not what you might last think. And the short answer is no, I cannot give a tight bound, but I can at least do better than what was already in the literature. It's just a sidelight. Anyway, so what? You sat here and listened to me blab for so far about 47 minutes. So what? And I want to give you an answer for two different hats. So as a combinatorialist, what I want you to take away from this is, well, sort of why am I excited about, well, it's not really about me, but like why am I excited about about causal set theory? Because physics asks a bunch of really interesting questions about locally finite posets that you would probably never think to ask as a pure mathematician. And that is actually the reason that I really like working in the whole area that I work in. I really think you get these really rich and surprising questions that you just wouldn't get from a pure perspective. And sometimes they're a little bit messy, and sometimes they come in a weird language that you have to decipher. But fundamentally, some of them are not messy, and they're just different, new, rich questions. Now, that I could say is true of many parts of mathematical physics. So what else? The other thing, another thing about causal set theory specifically, is it's not been overwrought yet. Like, it's not been worked over by tons of really famous people. It's not all worked over yet. So causal set theory is in fact a pretty niche approach to quantum gravity. So if you're off at the physics garden party and you're trying to impress all your physics friends that you're doing something super cool, you probably don't want to talk about causal set theory because it's actually like super niche, right? So, okay, maybe that's a downside. But the good side of that is it's not like 5 million of Witten's minions have already solved all the problems. So there's like stuff to do. I really think there's low-hanging fruit here. There's also the possibility to give back to physics, which is something I really enjoy doing. I really like it when I can solve something that at some level was just like a CO330 exercise, and like people in the community are super excited about it. I always think that's fun. As a physicist, so I already said you're not going to impress your friends at the garden party, so why might you be interested in causal set theory anyway? I think there's two answers. One is that the underlying axioms are just so simple and so strongly physically motivated. This is what I said at the beginning, that maybe it's not enough, but it almost has to be true. I wonder if I'm going to get flack on the video. You know, they turned off the comments because I got bad comments on my previous TUT, where like people who I strongly suspect are physicists came by and said that I didn't know at all what I was talking about because they didn't believe in formal power series, and like it was. But people will have, not every physicist is going to agree with what I had just said there. That's what I remember. And the other reason is because I hope that from these sorts of conversations, there's some renewed interest among mathematicians, and that's always a good way to make an area advance more quickly. So let's say new advances from renewed interest. by mathematicians. And that's why I'm excited about causal set theory, and I hope that I've convinced you that maybe you should be excited about causal set theory as well. Thank you.
Thank you. If there's any questions, please wait for the mic so that.
Sorry, thank you. If you take the complete bipartite poset and then remove a perfect matching, is the Minkowski dimension known for this case?
It is not known to me. I don't believe that's known. I think there's very little that's known. Yeah, I don't believe so. I think this is what I mean, that there are a lot of very accessible questions. And on the off chance I'm wrong, I know exactly who I'd ask to find out if it is known. It's a small enough community.
Thank you.
All right, well, let's thank Karen again.